In our next talk, Martin Keizer will cover some 5G security risks with focus on signaling interconnect messages, which would affect user privacy and expose networks in a similar way like its preceding protocols. May I please have your attention for 5G networks and interconnect threats?
Hello, my name is Martin Keizer. I'm working as a security researcher for Mobilium, and during this talk I would like to cover 5G mobile networks and the interconnect threats. First, allow me to introduce the company. So, Mobilium is a global company with global footprint, mainly providing the roaming and network solutions, fraud and risk testing, monitoring, mainly for the mobile operators and the carriers, but also security solutions like signaling firewalls, threat intelligence, and other products. I'm security consultant working for Mobilium. In the past I developed open source signaling firewall, did some Wireshark contributions, and also contributed to the GSMA security guidelines for mobile operators, covering SS7 diameter, GTPC and 5G protocols, and also did some Android development. Now, during this talk, let's focus on the interconnects. So basically, interconnects is something like private networks between the mobile network operators. Mainly, they are used to allow the roaming while the subscriber is moving between one country and another. And these are private networks compared to the internet, for example. And 5G introduced new architecture and basically new core networks also. So let's cover this. So basically there exists two models how the 5G could be deployed. One is called non-standalone architecture. Basically this means that the 5G RAN will be deployed, but the core network will remain the same. So this will be basically the evolved packet core 4G network, just the RAN will be 5G. In this scenario, the interconnection between mobile operators will remain the same, diameter, GTPC and GTPU. The second model is 5G standalone architecture, which means that there will be 5G RAN, but in the same time also 5G core network. And now if there would be interconnections between operators, there will be 5G interconnects using protocols like HTTP2 and GTPU. Here is just the overview, how it looks like. So behind the 5G new RAN, we can have 4G or 5G core network. In this talk, let's focus on the 5G standalone architecture, because from the security perspective, if there is 4G core, we need to apply the similar security like for the diameter security and GDPC security. Here is the evolution. So from 4G to 5G, there were several changes. So for the authentication and mobility management, in the past in 2G, 3G, mainly the SS7 protocol and with the MAP has been used. In 4G, this was replaced by the diameter, and in 5G, we will use HTTP2 to deliver basically the subscriber profile, authenticate the subscriber, and other messages. For the session management in 2G, 3G, and even 4G, the GTPC protocol has been used to establish the sessions. In 5G, also the HTTP2 will be used to replace the GTPC. For the user plane encapsulation, so basically where the IP packets are encapsulated between the core networks, basically always the same is used, GTPU. Regarding the network elements evolution, so basically these are the systems which are inside the core network. In the 2G, 3G, and 4G, we use the name like network element. In the 5G, because it will be service-based architecture, name network function is used. So we see that the network element names are now changed. In 5G. We will have UDM, so this is the main subscriber database storing the subscriptions of the users. MSC VLR in 4G and 5G, this network element is not there simply because the voice is not natively supported by the core. But IMS, IP Multimedia Subsystem, deliver the voice service. So the 4G and 5G is something similar like providing the IP bearer for the subscribers. SGSN or MME SGW has now evolved into AMF, SMF, UPF, so access mobility management function, session management function, and the user plane function. The GGSN or PGW in 4G is now in 5G, SMF, UPF. 5G regarding roaming and interconnects introduce significant improvement regarding the security. So now all the interconnections should be protected by N32 interface. This interface should be interface between the MNO to MNO, basically mobile network operator to other mobile network operator, and providing mainly the authenticity, so to prevent some message spoofing, integrity, that the messages has been not changed by some party in the middle, and also confidentiality, full confidentiality, or at least to protect certain fields inside the signalization. Here, on the network edge should be deployed SEP, basically, which is Security Edge Protection Proxy, and these network functions should basically terminate or establish the N32 interconnect. Regarding the N32, so it is divided into two separate, let's say, sub-interfaces. N32C, which is really direct SEP to SEP over TLS. This is basically kind of handshake and to negotiate on the security capabilities. And second is N32F. This one is to deliver actually the signaling messages after the handshake. So it can be protected by using TLS. This is something if there is really direct link from one operator to other, then we can rely on the transport security. And the second is kind of application layer security. This is basically PRINCE, protocol for N32 interconnect security. This was designed to allow also some parties in the middle, like roaming hub or some HTTP proxy, which can forward the N32 message, but basically still the mobile operators could secure somehow the messages with some signatures or integrity or even confidentiality of certain fields. Regarding all this, so keys should be exchanged between mobile operators, and this is covered by the 5G key management procedure. So it is public document GSMA FS 34, defining how the operators could exchange basically the keys to enable this 5G roaming. Current stage is manual, but in the future it is expected to automate the process. Here is just the overview. So it can be seen on this picture that N32C should be direct links between the operators, while N32F could be direct, or even could be go through, for example, some intermediate proxy from MNO2 over, for example, roaming hub towards the MNO4, and the similar even if there are two hops in the middle. In this way, still some MNO to MNO security could be provided, even if there are intermediate hops. Without this protocol, basically it will be more like hop by hop security, and the originating and terminating MNO could not really verify the messages or protect even by encryption certain fields. Still, even if this has been introduced in 5G, which is significant improvement, still there are possible attack vectors, and basically in this picture or diagram it is seen that if the MNO3 interconnects some third party and this third party sends some illegal message, still the message can be tunneled through the secure interconnection towards the MNO4 network. In this way, for example, the message can target MNO4 subscribers or possibly inbound roamers in MNO4 network, for example, which are not belonging to MNO3. So there is no reason why these kind of messages should be allowed towards the MNO4. This means basically that still there is need for application layer firewalling inside the protocol or inside the communication, and there is still need for some signaling firewall inside or after decrypting the N32. Regarding this, there exists document GSMA FS36, which performs some risk assessment and classification of the 5G messages. And additionally, for 5G messages, you can also refer to this public repository, and it includes basically Open API or the scheme defining the messages, which is very useful. 5G messages and interconnect filtering. So basically, the messages could be classified based on the way how they should be used. There exist also intra-PLMN messages only. This means that some messages should not be used between the operators and should really stay just within the same network. They are within the GSMA, they are classified as category 1, and these messages could be dropped when received from the interconnect. Then there are messages which need to be allowed, basically because we have the roaming between the networks. There could be communication from VPLMN, visited network, to home network, or in opposite way. These could be classified or are classified within the GSMA as category 2 and category 3. Additionally, in 5G, there could be also other messages like network to network communication, even if there is not involved subscriber. And, for example, also in later releases, there could be SMS service, and this is more like A party to B party communication. So it is a bit different than the roaming situation, and also other messages. Regarding your testing, or if you're interested in testing 5G and set up some lab environment, you can use these projects. So one is free 5G Core. So it is open source project. Second is GNB Sim, basically 5G run simulator. This is useful that if you are not willing to use real physical SIM card with some card reader, how you can attach basically or simulate the attach of the UE, which can be useful if you are willing then later on to test, for example, some HTTP2 messages towards the core. Regarding the client for testing, so basically you can use or you can try to use open API generators to generate the client and the server for you. Other way is really just to write your HTTP to client directly for the testing, basically without the generators. Regarding the limitations, so free 5G Core, currently there is no SEP or no OAuth authentication of the NRF. Regarding the setup, so you can do something similar. For example, install Ubuntu VM, inside deploy free 5G Core, and install GNB Sim. Then from the host or even directly from the Ubuntu VM, you can use your HTTP2 client to inject the messages. and send it and test it towards the core. So on the left panel, you see just the examples of the running of the wall. Regarding the open API generators, so if you are familiar with previous generations and protocols like SS7, there was used ASN1, like abstract syntax notation, which was basically some kind of scheme. And based on this, you were able, by using ASN1 compilers, to generate the encoder or decoder for the payload. Something similar is used for the HTTP2 and OpenAPI. So basically, this define or prescribes the messages, how they should look like, how the API should look like. And after, you can compile your code, which will create some skeleton of the client and the server. But alternative is also you can write your custom client. Why? Mainly because HTTP2 and JSON messages are really easy to encode, and there is no significant hex or byte encoding like in SS7 there was BER, or some TLV encoding in the diameter. Here is simple example of HTTP2 Python client. So it is really easy. You can open the connection towards the target IP address and port using the HTTP2, and then just send the GET request, for example, for target URL, and something similar for POST. So you will just define the target IP, port, POST, URL, and then the payload. So basically inside is the JSON. Additionally, you can specify, for example, the message headers. And then you read just the response back. Now, let's imagine that the free 5G core is some real target network, and we can imagine that by using our client, we will try to inject some messages towards the target PLMN. So we can start maybe with one example. This is search NF instances. The client or the producers of these messages should be basically network functions or SCP or NRF, and consumer is the NRF. NRF is some network element which acts as some registrar function that every network function should register towards the NRF, and NRF also provide the information what network functions are registered there. So it works basically in both ways. There is also a possibility that the one P element to other communicates. There is NRF to NRF interface, and basically it can query also what are the target network elements. So you can see that we can craft easily message HTTP GET towards the target URL, and there we have we are acting like AMF and querying the NRF and asking, please provide us the UDMs in the PLMN network. Now, here is just the overview how it can look like. So we can receive this message from one MNO1 towards the MNO2 and reaching the NRF. Here, basically the impact will be topology discovery and how the response looks like. So this is just capture from the Wireshark that after sending our GET request, we receive 200 OK and the payload back. And we can see now we have also all the details like IP address, NF instance ID, and even service name. So all the APIs which are supported by the target network function. So this can be useful to perform some network discovery, topology discovery of the target network. Other example of additional message is the register NF instance. So here, this message it is produced by network function or SCP towards the NRF. Now the difference is that the register or registration should be done within the intra-PLMN only. So for example, if such message is received through the interconnect, it should be blocked to prevent some not wished behavior in the network. Here we can see how it is easy to grab the message. So just sending the delete regarding or towards the target URL, and here should be some NF instance ID. This we can retrieve through the search as seen on the previous slides. Here is just the global picture, like one network can send it towards the other network, send the register target NF, and possibly can maybe disrupt the service that the NRF will be not able or will be not consider the target network function as registered anymore. Other example of next message is get free GPP registration. Now the producer is network exposure function, consumer or the targeted system is UDM. There is not much description in current free GPP releases, but it is intra-PLMN message only, so it should be not normally allowed from the interconnect. Example is quite simple. We can send the HTTP GET towards the target URL, then there is the IMSI, and we are asking for the registration of AMF free GPP access. And here is the global picture, like one network can send this message towards the other network. Here we have our UDM. And by this message, basically, attacker can retrieve the subscriber route location, like what is the current AMF serving the subscriber. This can be some precondition for later attacks, so we will see it on the following slides. Here is the example of the free GPP registration, get free GPP registration response. So we can see that MCC, MNC are provided. Then we see the AMF instance ID. So all the information which can help us to identify really the exact AMF which is serving the given subscriber. Now provide location info. So here producer is the UDM, consumer is the AMF, and we have some free GPP description. Here the HPLMN communicates towards the VPLMN, and this is basically normal service that the GMLC should be allowed to geolocate the target subscriber. The illegal scenario is if the different network, then what is not the home network of the subscriber is trying to geolocate the target. Here is also the example request, so we can see that we just inject the post towards the target IMSI, and requesting all information what we can get. Now here is the global picture. Again, MNO1 send this message towards the MNO2, towards the AMF to retrieve the exact cell location. And now how the response looks like. So we can see there is quite everything. We can see there is MCC, MNC, and we have also cell ID and the UE location timestamp. So basically, cell ID can be later translated into exact geolocation, like longitude, latitude of the subscriber, and we can really precisely track the subscriber. Why this is somehow risky? Mainly because what we see currently in SS7 or diameter in the existing networks, there are really active surveillance by some surveillance companies or state even agencies using this as a way to geolocate the phones, geolocate the subscribers actively, and this can be expected also to happen in the 5G. Regarding implementation specific vulnerabilities, so the above was mainly covering some generic cases according to specification if there is some lack of the filtering. Now, of course, depending on the implementation of the target 5G network, there could be also specific vulnerabilities like parameter injections, even SQL injections, JSON deserialization attacks, buffer overflows, OAuth issues, lack of maybe granular access control, access token abuses, and even others vulnerabilities which can be really implementation or even deployment specific. Here is just a free 5G core example of some injection of the parameter by crafting or using the following request. So basically sending the HTTP GET towards the UDM, we can inject the parameter PLMN ID, and as you see, it is not properly formed, so it is not some MCC, MNC there, but really message name. which is later on used by the UDM towards the UDR. Here is also trace. What is here? What can be seen? So we can see that by sending this message with the injection, after UDM sent towards UDR different message, which was not expected, like authentication data, authentication subscription, which is actually querying the AUC data, and then the UDR responds back with the AUC data. Fortunately, towards our HTTP client, the response from UDR was not forwarded. Why this is risky? Because normally the UDR should be not directly accessible and should be accessible only internally within the PLMN, not from the roaming. So this is kind of exposure and something new in 5G, that now even the AUC can be somehow reached through specified messages. And here is the flow, how it looks like. So basically the HTTP2 client was sending the message with the injection towards the UDM. UDM was not properly sanitizing the parameter and just forwarded it towards the UDR. This means that the UDR interpreted as a different message and sent back the query authentication subscriber data response. Fortunately, the UDM did not forward the message to our client. Here I opened also GitHub issue for this to basically fix this. This is just an example of some vendor-specific vulnerabilities which can be really introduced by the implementation, and it can be really dependent on the target technology. Here is also example of other risky messages. So all these APIs it really depends what the target network will support. If it will be like release 15 compliant or release 16 or even more. And here is examples of some additional geolocation messages, or even there could be done the impersonation like ROGU. We can register basically ROGU AMF towards the UDM or ROGU SMF, and later on this can be abused. Then also there would be SMS messages, so we can see maybe some SMS spam or spoofing, and there are plenty of other messages. You can check the open APIs, so there are really plenty of messages and quite significant attack surface. And now regarding the conclusion, so basically in 5G, the significant improvement is that the interconnects are really confidentiality, integrity, and authenticity has been introduced on interconnects. The N32 and even N9 should be protected. However, regarding the signaling attacks, this still could be received inside the N32 tunnel, and therefore we need some application filtering. And in 5G still the security controls which would be needed are signaling firewall, signaling intrusion detection systems. Basically this could be separate system which continuously audit if the firewall or other filtering is efficient and if it is working properly. Threat intelligence to see really the global picture, who are the sources of the illegal activity, or what really attacks are being exploited in the wild, and which are more maybe just theoretical one and which are really threat to the networks, and then some regular vulnerability scanning and security audits. So thank you very much for listening to this talk. Feel free also to contact us or contact directly me, and we can try to provide answers. Thank you very much.
welcome back to the COMMSEC track where we are about to break stuff. In an attempt to secure the many PLC units controlling the world around us, Siemens has designed the PLC protection mechanism. In this talk, Gao Jian, a researcher of industrial control system security at Jiwu Lab, will talk about his findings after researching this system. Without any further ado, over to Gao Jian with Breaking the Siemens Symmetric S7 PLC Protection Mechanism.
Hello everyone, this is Gao Jian. I'm very glad to be here and share my research findings at HITB today. Really appreciate the opportunity. The topic I would like to share today is Breaking Siemens Symmetric S7 PLC Protection Mechanism. Before I begin, I would like to introduce myself real quick. My name is Gao Jian from Xi'an, China, currently an industry control system security researcher at NS Focus. The research mainly focuses on PLC, DCS, SCADA, industrial equipment, and system. Working includes things like vulnerability modeling, industry field security testing, and evaluation. For the past few years, I have reported several vulnerabilities to Siemens, COMMSEC, Schneider, and so on. Got dozens of CVEs and of COMMSEC notes from these companies. If you have any questions or ideas regarding the security aspect of industry control system, please feel free to contact me. Here is my email. I'm looking forward to your emails. So, here is the layout of today's presentation. First of all, I will give a brief introduction of Symmetric PLC and its application series, including what series of Symmetric PLCs have, what a PLC protection mechanism is, and why I want to break them, what possible implications are after breaking the mechanism, and so on, followed by more detailed explanations of how to break the protection mechanism according to different series of products. Okay, let's get started. Symmetric is a PLC produced by Siemens for industry. There are several Symmetric series products, like S3 and S5, but they were outdated and withdrawn from the market. The latest series now is S7, which has been the most popular PLC in the market and used in areas of critical infrastructure, such as energy, power grid, water, automotive, manufacturing, and other scenarios. Symmetric PLC has a variety of built-in security measures, and we will look into ones regarding access control protection today. Access protection provides comprehensive protection against unauthorized configuration changes. Authorization leaves can be used to against separate writes. Access protection provides comprehensive protection against unauthorized configuration changes. Authorization leaves can be used to assign separate rights to different user groups. Different authorization group has different authorization leaves to perform different activities. Breaking the authorization group boundary will allow us to perform sensitive activities outside of our authorization leave, like application downloading, uploading, starting, and stopping of the controller, which are all designed to be secured by high-level authorization leave, and misconducting them could potentially lead to business failure. In addition, bypass the authorization could let us guide the core application program for the controller, which may be the most valuable patented techniques and core competitiveness. on a company. If the content requests are acquired by its competitors, it's devastating for the company. So, for whatever reasons, the access protection mechanism is brushed. All related activities, devices, and even our physical life could be potentially at risk. First, let's take a look at the S7-200 series, which has a Chinese version with Level 4 password protection. At this level, we can't upload the application program even with a correct password. So it's supposed to be a quite secure mechanism regarding the protection of the core intellectual property. But there is always a way to bypass it. Let's see how. After some analysis, we understood that there are several steps in the Level 4 protection mechanism. First, we need to set a Level 4 password in the system block, and then calculate a ciphertext using a specific algorithm. After comparing, the result is downloading, use PPI protocol, and then save into EEP-zone chip. Now that we know the password information is in the EEP zone, the general idea is decoding it, reading information out of it, changing the password level byte, loading the key parameters of the original system block to the computer, and mission accomplished. Let's take a look at it in more detail. The picture on the left is a screenshot of the EEP zone, and in the middle is our self-made debugging toolkit, so that we could frequently read from and write through EEP zone with ease. The diagram on the right is the content of EEP zone. After analysis, we found the best for its password level, as shown in the red box here, a 04 access level, and bytes for the encrypted password, as shown in the blue box here, the encrypted 你好123 password. However, thoroughly altering the password level byte so that we have a level 1 instead of level 4 is not enough to bypass the authorization, since the PLC uses another 2-byte verification in EEP zone, which is familiarly completed jailbreak. But we have a smarter idea to bypass it. The idea is let itself solve the problem. We can extract the parameters of the system block from the original bin file, fabricate a client to encapsulate the parameters to PPI message and install it back into PLC, so that PLC can go through the verification procedure. Paired with the password level byte change, we now bypass the level 4 authorization and get the core application inside in the PLC. Now let's take a look at Siemens S7-200 Smart PLC, designed for Asia market. For this series of PLC, we performed a man-in-the-middle attack. To stop the traffic between the PLC and the configuration software, we try to decipher the hidden information embedded in the traffic and found something quite interesting. We try to decipher the hidden information embedded in the traffic and found something quite interesting, which will help us guide the password, hence brush the access protection. First of all, we still need to know the algorithm of its authorization. or how its password protection is implemented. After some research, it's found that there is a four-step challenge response process. First, the client initiates the process and requests the POC variant number RK, and then the POC returns with a 22-bit challenge, and then the client sends the response a calculated 20-byte hash value, and finally, the POC rifles the challenge response pair and returns the corresponding result. Since the 20 bytes hash value can be obtained from the traffic, we then need to know what algorithm is used to get this value. Provided with the 22-byte POC challenge and the password set by the user. To do that, we reverse the COMMSEC.dll in the step 7 microvin configuration software. After analysis, the algorithm is like this. There are three key variables: the input, password, and 22-byte arcane returned by the controller, and the hardcode key stored in the controller. The first step is to do a SHA-1 calculation of the password and the first 2 bytes of the arcane, get X. The last 20 bytes of arcane are Y, and XY is used as input parameter. The first 2 bytes of arcane are used to replace the 13 and 14 bytes of the hardcode key inside the POC. After the replacement, a new hardcode key is created. Finally, to get the 20-byte hash value, we use X, Y, and the new hardcode key to perform a HMAC SHA-1 algorithm. At this point, we have the 22-byte arcane, the hardcode key, and the 20-byte hash value, and I have implemented a script to calculate the hash. Then we try to breach the access protection by cracking the user input password with an offline brute force attack. So the whole process would be sniffing the traffic to the locate the authorization information and then brute force the password. We have tested that a 6-digit password only took about 17 seconds on a normal PC, so it's quite feasible. Okay, S7, 300 and 400 is the most widely used large POCs in the industry field at present. They are mainly used in the control of critical infrastructure, such as the storage, melting, oil depot management, and other screens. Access control protection of its series has been cracked through the past few years, with online brute force attacks and corresponding tools have been released. What we are going to talk about today is finding mystery information through the protection projectiles and use the information to break through access protection mechanism. First, we found HITBSecConf2021.dbt field in the project field, from which we found the cipher text. We found the corresponding encryption algorithm by reverse the step 7 and 7 HITBSecConf2021.dll field, as shown in the diagram on the right. This algorithm is a simple XOR encryption, and ciphertext information is obtained through XOR encryption. Then, we can write a corresponding decryption script feed the ciphertext to get the corresponding plaintext password. Once we get the plaintext password, we get the direct access to the S7, 300 and 400 PLC controller. Finally, let's take a look at the S7 1200 series, which is the most secure series of the whole Siemens PLC products. Its latest version, V4, is a high-end PLC in China with more comprehensive security features, and its access protect mechanism differs from other series. The S7 1200 PLC has 3 different passwords with separate permissions. Any action with a certain permission level can only be granted with the corresponding permission level password. Similarly, the overall security of the S7 1200 series is very strong. The 32-byte integrated verification mechanism and the communication protocol S7 compliance are protected by a variety of mechanisms, which can't be bypassed using the similar technique we mentioned before. However, we use passing the hash attack to deal with this situation. This attack was very effective for breaking the access protection of the S7 1200 series. Here is how we did it. First, the first step is to get access to the S7 1200 memory, which can be done in 2 ways. The first is exploit vulnerability and use a tool to dump out of the memory. This vulnerability is likely to be a hardware fault which can't be fully fixed. With the special access function of UART, we can create a script to read out all the contents of a given address and save them. And hence, we will have the memory of the device. The second method is hardware desoldering. The NQ281 chip that stores firmware and application data can be soldered, and use a logic program to take out all of the content. The second step is to look for key information from the memory retrieved in the first step. The memory of S7 1200 has a total of 128 MB, which starts with the bootloader followed by the firmware and application data of the device. We analyzed the latest firmware version of S7 2015C in detail, May 2021, and obtained its code segment, read-only data segment, and starting address and length of the data segment. The corresponding decompiled pseudo code is also obtained by loading the code segment content using IDE. The third and the most important step is to find out exactly where the password is stored. After the reverse of the core process module OMSP core manage.dl, it found that the password is stored in the form of SHA-1. The HMI access protection password 20-byte hash, read access protection password hash, full access protection password hash. All of the password hash are stored in the memory of the BSS segment in exit order. At this point, when the password is set to none, you can locate it in the BSS section, which starts with the null passwords SHA-1 characteristic DA39A3 If all passwords are not set to none, you can start from where most of 0000s and look for 20 bytes of the SHA-1 feature that preceded them. Once successfully located the 20-byte hash, we could mount an X34DBG on the configuration software TRA to locate the password encryption process. We then replace the run hash directly with the 20-byte hash. We fill in the memory to perform pass the hash tag. In this case, we could breach the S7 12-header access protection mechanism. The following is a demo of the attack. First, we create a new project and upload the application program on the PLC to be brushed. And then we mount a X74DBG into a random password. Continue the process till we hit the breakpoint where the password encryption happens. Replace the 20-byte hash. Continue the process. Now, we have successfully used the tag to bypass the protection and can then perform the desired action like uploading applications, stop and run the PLC controller. Okay. In May 2021, Siemens released the latest firmware version V450 for S7 12-header series. The version addressed a lot of security issues, such as enhancing the encryption of CPU access new password, encrypting PLC configuration data, and using TLS to achieve secure PGBC and HMI communication. However, we found a very interesting thing. We have a S7 1215C firmware upgrade to V450 version. An application with access protection was configured and installed into the upgrade PLC using TRA V13. At this point, if we need to upload an application or create a new project using TRA, a password input box should pop up and let us enter the correct password. However, when we upload the application, TRA didn't pop up any authorization interaction and just upload the application with the password. We don't know why this happened, but it was clearly a bug. Without any great details, we could get access to the password-protected project. We have gone through the firmware update information of Siemens in detail, which mentioned that the firmware with enhanced security feature must cooperate with the Step 7 V17 basic software in order to verify whether the latest version TRA V17 and firmware V450 also suffer the hash parsing attack. We need to find the software for Step 7 V17 basic. Unfortunately, as of May 20, 2021, we have yet to find the official download address or any information on this software. If you are interested in this issue, feel free to contact us for future information and discussion. So far, we have covered several access protection faults and ways to break the protection mechanism. But as PLC manufacturers, how can we enhance the access protection security features to prevent such attacks. Let's start by looking at ways to enhance security from the configuration software. First, server code protection techniques can be added to improve the difficulty of resolve energy, such as code obfuscation, or adding a high security shell for the software. The second is to introduce the idea of neutral authentication, so that the PLC and the configuration software is verified neutrally. The third is to use the encryption technology to strengthen the protection of protect fields, because sometimes protect fields are an attacking vector that we often overlooked. With protect fields, one can obtain the password information, which can be used to brush password protection like we shown in the above S7-300 example. Let's take a look at some ways to enhance security from a PLC controller. First, sensitive information should be stored in the trust block, which can be reinforced by software or hardware. For example, encryption keys, challenges, core algorithms, and other information should be placed in the trust block to prevent it from being easily obtained by malicious attackers. The second is to add neutral manually. The second is to add neutral authentication between the client and the PLC, so that the client and the PLC controller are authentication neutrally. The third is mandatory password strength settings. This is very necessary at this stage in the industry since few people set passwords for PLC or only set weak password, which can be easily cracked by brute force attacks. A false strong password can prevent such attacks. The fourth point is to add physical hardware protection techniques, which is the simplest and the most feasible way to prevent the hardware design technology from being stolen and the core information from being obtained. The above mentioned are common methods of protection. We are sure there are much more. This method can be used in the design of PLC and its client software. Use this method, it can effectively prevent much of the obvious breach of the access protection. It will also make our and PLC users feel more confident and secure, and will prevent some unauthorized attackers on our critical infrastructure. But it's a marathon, and only consistent, vigorous, and comprehensive protection can ensure that our critical infrastructure are safe from attacks like the Ukraine power outage. Okay, that's all for today's presentation. Thank you all for joining the talk. If you have any question, please feel free to contact me. Bye-bye.
For our next talk, Theo will be looking at how malware can maintain a covert communication channel without being detected by popular and IDS systems, and will move on to how this would work in a current-day cloud environment, evading AWS Guard Duty detection. We present AWS Guard Duty, post-DNS era covert channel for CNC and data exfiltration.
Hi, thanks for joining this presentation. I'm Theo. Today I'm going to talk about covert channels for CNC and data exfiltration techniques to evade guard duty detection. Before I start, I would like to mention that the contents expressed in this presentation are solely my own and do not express the views or opinions of my employer. So who am I? I have presented at Hack in the Box 16 years ago, and I'm glad to be back again this year. I spent most of my working years as a software developer, then moved into sysadmin DevOps kind of role, and eventually transitioned into an InfoSec guy. If you want to reach out to me, this is my LinkedIn ID. Here's the list of items I'm going to talk about today. We will start with an overview of DNS tunneling, network IDS, host-based IDS, and SIEM. Then we will explore and improve covert channel technique that makes use of popular cloud services. After that, we'll take a look at how Amazon Guard Duty works compared to IDS and SIEM, and also the techniques that we can use to evade detection by it. This is followed by a proof of concept and live demo. Finally, I'll talk about some of the common mistakes that people make when using AWS along with the mitigation tips. First, let's take a look at the timeline of different command and control channels used by threat actors in the last 3 decades. During the 1990s, there were many Unix hacking tools distributed in the form of Perl scripts and C source code. As far as I can remember, they are usually distributed on those Frag magazine websites. If some of you here are old enough, you probably might have heard of red tools like NetBars, Backorifice, and Sub7. Most of the Linux and Windows hacking tools that time were using direct TCP for CNC communications. Back then, networks were simpler because every computer that is connected to the internet gets an individual public IP address. I remember during the late 90s, Sub7 released an updated version that started to use IRC channel for CNC communication. DNS tunneling was introduced around the same time when Oscar Pearson shared his proof of concept on Bugtrack mailing list. For many years, HTTP protocol is used by most malware as the CNC channel to communicate with the attacker's server even today. Until 2014, we started to see reports that Reddit, GitHub, Twitter, and Instagram were being used as the CNC channel. However, these are mostly CNC channels used by malware that run on the end user's personal computers. Most of these CNC channels will fail to work when it comes to corporate servers with strict firewall outbound rules. Among all the mentioned channels, the only technique that is tricky to block is DNS tunneling. When a compromised host wants to communicate with the attacker, it doesn't need to send a direct DNS query to the CNC server. Instead, it sends the DNS query to any trusted recursive DNS server used by the host, just like any normal program would do. What happens is the attacker has already set up a domain name and hosts it using their own authoritative DNS server. So all uncached queries for the attacker's domain name that is received by any recursive DNS will eventually reach the attacker's authoritative DNS. This makes it difficult to block DNS tunneling, because there is no way a firewall can tell if a DNS query is legitimate or malicious. From the firewall perspective, it can only see that all DNS requests are being sent to the same recursive DNS server. The reason that DNS service cannot be blocked because applications needed to resolve external hostnames for various reasons. such as to pull OS updates or access external APIs and so on. Nevertheless, the standard DNS protocol is not encrypted. So DNS exfiltration and CNC activities can be seen by network IDS. What about DNS over HTTPS and TLS then? Well, it depends on what kind of environment we are looking at. Covert channels using an encrypted protocol in corporate office network can be difficult to detect when they use port 443. Because any users can be loading a website via HTTPS protocol. For server environment, encrypted DNS can be detected in the same way as any other suspicious HTTPS traffic with SIM. This is because data exfil activity can cause a sudden influx of outbound HTTPS requests to an external IP, making it stand out from the other traffic. In this talk, we will mainly focus on evasion techniques in the server environment. Some organizations deploy network-based IDS like Snort, Zeek, or Suricata. These solutions work like Wireshark by picking into all the network packets that flow through them. The detection is not foolproof because they use signature databases and rules to check the packet headers and content. Besides, it has limited insights on encrypted traffic like HTTPS, so it can't tell whether a request is GET, POST, or PUT, and to which URL accept for the IP address. Also, deep packet inspection doesn't scale very well when it comes to networks with high throughput. Another type of IDS deployed by some organizations is the host-based IDS. This type of IDS works by installing an agent inside a server to monitor and analyze various areas like file system integrity, process creation, network connections, and application logs. It is usually difficult to evade detection from it unless you can gain access to the host through some sort of code execution within the same process memory of the compromised service. However, host-based IDS is not widely deployed for a few reasons. For example, there are concerns on performance impact and stability on the host as some of them uses kernel mode hooks. This type of hook can sometimes cause problems to certain applications or crash the whole system if it is buggy. Host-based IDS is usually not very platform agnostic due to the use of kernel modules. And some organizations have servers running very old Red Hat that is no longer supported. In Windows, kernel mode hook is no longer allowed since 64-bit due to patchgut, and Microsoft requires kernel drivers to be signed before it can be loaded by Windows. Another problem with host-based IDS is that it can get quite noisy due to rapid application changes in modern software delivery process. Nowadays, many organizations prefer to use SIEM over IDS, but of course, they both can work together as well. SIEM, in my opinion, it is more powerful as it works at a higher level on top of various data sources. For example, we can feed it with the logs from VPN, AD, DNS, web applications, and endpoint security like antivirus. Then it can aggregate those data to provide insights like traffic patterns for anomaly detection. Alerting rules and actions can also be configured on top of these insights to block an attack automatically. It is essential to have SIEM because it can simplify investigation during a security incident and identify the scope of a data breach, especially when you need to comply with legal requirements like GDPR. We have briefly gone through how DNS tunneling, IDS, and SIEM works. Now we'll take a look at an improved technique for the covert channel using popular cloud services to evade detection. Most organizations today use some sort of cloud services like GitHub, New Relic, Cloudflare, and so on. For example, if an organization uses GitHub, their CI/CD servers would need to connect to GitHub to fetch the application source code during the build process. The same thing applies when an application needs to send or receive data from any other cloud services. Due to this reason, The IP range of these cloud services are normally whitelisted in their SIEM and allowed by their firewall. To see how these trusted IP addresses can be used by malware, we will need to work backward. Assume that we're the attacker, and our target for data exfiltration is a server running in a secure network. That server sits behind a firewall and does not have any public IP address. The only way it can reach the internet is through a NAT gateway. And that server uses the internet to fetch repositories from GitHub and get OS patches. Let's say we're going to use to compromise that server through a supply chain attack. Before the attack, we'll need to prepare a few things. First is to gather the IP range of the popular cloud services. We don't have to gather the IP range of every cloud service, but we need to pick them based on a few criteria, like look for those that are widely used by many organizations, then check and see if they have their API and IP range documented publicly in their website. And most importantly, the service must have the ability to store and retrieve data. Second, we also need to select a few popular CDN services and gather their IP range. Third, we have to create accounts for these selected cloud services to obtain the API keys for using them, and also set up our CNC server behind the selected CDNs. The last step is to embed the API keys and collect the IP range data into the supply chain malware for later use. In the supply chain malware, the way how it establishes the CNC channel is the crucial part to evade IDS detection. It needs to monitor all the operating system connections for at least 24 hours and continuously look for any remote IP address that matches any of the embedded IP range data. This should be done as often as every 1 to 2 seconds, but it is a very lightweight operation, so it's not going to cause any CPU spike. On Linux, this can be achieved by reading /proc TCP as a file, /proc TCP, procnet TCP as a file, sorry. While on Windows, the same information can be retrieved through get TCP table API call. If there is no matching IP address found after 24 hours, the next step is to look into the operating system's package repository config. We want to look for a hostname with IP address that matches any of the embedded IP range data. So now we have 3 possible outcomes. First, if a matching cloud service IP address is found, then the malware can use that cloud service storage as CNC channel to exchange data. Second, if a matching CDN H IP address is found, then the malware can use that CDN endpoint to talk to the CNC server that was set up previously. And third, if there is no matching IP address found, just default to any of the selected CDN. And the malware will have to use the endpoint of that CDN to talk to the CNC server. The first 2 outcomes will blend in the CNC traffic as legitimate SAS usage. This can help to stay invisible from the IDS and SIEM detection. The third outcome might potentially trigger IDS or SIEM alert, but there's a high chance it may be treated as a false alarm. Why? Because when the SOC engineers see an IP address that belongs to a reputable CDN, they might think it is some applications downloading updates that is being hosted behind CDN. I'll now talk about the main topic of this presentation, guard duty evasion. Amazon Guard Duty is a managed threat detection service from AWS. According to the AWS website, Guard Duty works by analyzing data source from CloudTrail, VPC, flow logs, and DNS. It also uses threat intelligence feed and machine learning to detect anomaly in the AWS account. And one important thing to keep in mind is IAM is used everywhere to call AWS API. Now let's assume that our target for data exfiltration is a server running in AWS and all dependent services are AWS products. To avoid guard duty detection, The malware must not call any API service using the compromised host's IAM credential, so we don't leave any trace in CloudTrail, and we don't want it to communicate with any IP address that is not trusted by AWS. Also, we can't use DNS to perform data exfiltration since GuardDuty can detect that. So what do we need to establish a CNC channel while making sure GuardDuty is happy? We need a medium for data exchange between the malware and CNC server that doesn't require AWS API. That medium for data exchange must be trusted by AWS to pass GuardDuty's check. The implementation should be simple enough that we don't need any extra crypto libraries for authentication. And it should use HTTPS protocol to blend in, like performing a usual REST API call. Actually, there are many options to evade GuardDuty, but due to time constraint, I'll show 3 of the ways to do it. First option, embed the IAM user access key of the attackers in the malware. This method allows the use of any AWS resources like S3, SQS, DynamoDB, and so on. It is similar to many malware CNC channels, except that the malware interacts with AWS endpoint instead of some unknown IP address. The disadvantage of this option is when someone found the access key in the backdoor code, they can use it to get the AWS account ID and IAM username. Then they will straight away know it is a backdoor the moment they discover that account ID does not belong to them. And this method requires HMAC and SHA-256 algorithm to sign the API request, but it is not ideal to add more code or additional dependency in the backdoor. On a side note, this method will not generate CloudTrail log in the compromised host account because it is using the attacker's access key. The second option is to set up the CNC server hiding behind the Amazon CloudFront CDN. This method does not require signing the request, but the chances of getting detected by GuardDuty is unknown. I've only done limited tests and GuardDuty did not detect it. However, we don't know if GuardDuty might start flagging outgoing connections from EC2 to CloudFront in the future. Amazon Linux 2's YAM repository is hosted on S3 directly, so S3 will be a more trusted service than CloudFront. The next option is to use the attacker's S3 bucket with pre-signed URL. This method does not require signing the request as well, and S3 bucket is preferred since Amazon Linux 2's package repo is using it. Although S3 pre-signed URL has limited validity, but we can work around it. This is the most preferred option among the 3. And let's take a look at how our proof concept uses this approach. Before I proceed to the demo, let's take a look briefly how it works. In this POC, we use a S3 bucket as the medium for data exchange between the compromised host and the attacker. First, the attacker starts a CNC service by generating pre-signed URL as channel files that can be accessed publicly by the malware. The service will keep refreshing the pre-signed URL in these files every 24 hours to maintain its validity. At the same time, the service will also poll the bucket periodically for any session creation request files. This is shown in step 3. Basically, the CNC service is now running and waiting for any compromised host that tries to communicate with it. In step 2, when the malware starts running in a compromised host, it will randomly pick one of the channels and use the pre-signed URL to create a session request file in the bucket. Now the step 3 at the attacker's side sees the session request. It will create a private session based on the session ID picked up by the malware. As the new private session ID is created, the malware will now poll for server message using the session ID as shown in step 4. So any messages from the service will be executed by the malware in step 5. And the output is then written back to the bucket with the pre-signed URL. So in the final step, the service will read the output from the bucket to display, and it repeats the whole cycle all over again. Now let's look at the demo. So in my AWS account, I've created this bucket named HITBSecConf2021 AMS bucket, as you can see from here. This is the S3 bucket that will be used for data exchange. So here are my proof of concept codes, and now I'll run this CNC server on my local machine. As you can see that, okay, this is my local machine user. So now the service is started on my local machine, and it is making use of the S3 bucket as the data exchange medium. Before I SSH into the EC2 that I'm running in AWS, let me show you the guard duty status. So I did a refresh, and we can see that the last seen findings is a day ago, and these are all the sample findings that I generate using the guard duty tool. Now I'm going to SSH into my EC2 instance to run the proof of concept malware. Okay, as you can see, this is the IP address that I've created an EC2 earlier, which is here, 3.250.87.30. And this is running in AWS. And earlier I've prepared a file, this CNC client oversheet. I can show you and take a look. So it is kept as simple as possible, only using a HTTP client. And yeah, the proof of concept code can be obtained in the link that I provided in the slide. So the moment I start this CNC client, it will start to establish the session via the S3 bucket that we've created. As you can see that the session has been established now, so it's basically just waiting for a command from the attacker, which is on my local machine. So on my local machine, this CNC service is basically like a reverse shell. Whatever command that I type here will be executed on the malware host. So let's take a look. So you can see that the uname-a, it goes over here on the remote host, and I get the output redirected back. To show again, I'll run who am I. My local user here is Jacko, but on the remote host is EC2 user. And okay, let's check the DSpace. And also list the files in the current folder. This proof of concept can be modified easily to perform file transfer as well. Now let's take a look at guard duty again. We can see that there's no new findings here, even though I refresh, and the last seen is the one that is a day ago, because guard duty it doesn't detect any actions to or any read or write activity to S3 bucket as malicious. It may take a few moments for guard duty to process the logs like VPC flow logs, DNS logs, and also like CloudTrail. So we'll come back again later and take a look again. Let's move on to the final slide. Basically, here are the common fallacy about AWS. First is that many AWS users believe that it is safe to allow all egress traffic to AWS services. The problem is, remember that AWS is a public cloud. Most of the managed resources are shared among different customers. In fact, tightening egress traffic is as important as tightening ingress traffic. So by using AWS private link endpoint, we can restrict the traffic to a specific bucket through the endpoint policy. This will help to protect your host from S3 exfiltration, which makes the earlier shown technique won't work. The second fallacy, using IP tables in EC2 is the same as security groups. This is not true because IP tables of a compromised host can be changed if the attacker got root access on the system. But security groups works at AWS account level outside of the host. Also, when security group is tempered, it can show up in CloudTrail. This allows us to write Lambda function to monitor CloudTrail for any security group changes and trigger alerts whenever necessary. Therefore, it is recommended to use security groups over IP tables. And the third fallacy, having guard duties enough for overall security monitoring. Amazon Guard Duty is good in monitoring a subset of security issues, maybe like 70 to 80% of common threat. Unfortunately, a lot of data breach can happen and stay undetected for years due to the missing visibility of that 20%. So in order to achieve good security visibility, it is essential to continuously tweak and improve the SIEM in your organization. Now let's take a look at the final, do a final check on the guard duty to see if it detects my S3 exfiltration demo. So I'm doing a refresh again, and we can see that there's no new findings at all. Well, a final run, we can see that, okay, the uptime, yeah, it's basically still running fine with no detection. So yeah, basically that's all for my presentation. And I'm going to shut this now. See, it got disconnected and shut down the instance. Okay. The proof of concept code can be obtained through this link, github.com/ssto HITBSecConf2021 AMS-POC repository. And that's all for my presentation. Thank you.
And now we move on to what is already the last COMMSEC talk of this event. Dagmawi Mulugeta will be presenting the server counterpart to JA3 transport and a few methods of evading JARM-based fingerprinting and provide a JARM randomizer proxy to thwart any JARM-based block lists. Please enjoy JARM, evading JARM fingerprinting.
Hi, and welcome to Hack in the Box 2021 Amsterdam. I hope you're doing well, and you're excited to be learning about TLS SSL fingerprinting and overcoming it. Today we'll be talking about JARM Randomizer, which does exactly that. So let me start by introducing myself. My name is Dagmawi Mulugeta. I am currently a threat research engineer at Netscope. Previously, I've held positions as a researcher, software engineering, and developer at multiple companies. I have my master's in cybersecurity from Drexel University, and my interests span capture the flags, exploit development, and abuse, and general research of cloud applications as well. Cool. So let's talk about what the rest of this talk is going to be. We will start the goal of this presentation is to talk about SSL and TLS fingerprinting and take a look under the hood of JA3 and JARM. And then we'll talk about how JARM fingerprinting particularly isn't bulletproof as a lone tool. And then we will segue into how miner-side, server-side changes or configuration tweaks result in different JARM fingerprints. And finally, we will package all of this up and present or provide a tool to switch between these configurations to return a different and desired JARM signature. Cool. So let's start by talking about what JA3 and JARM are. To do this, we need to take a step back and talk about the TLS or SSL handshake. So TLS and its predecessor SSL are generally used to encrypt communication between applications like internet browsers and target servers, right? So typically when you type in your username or your password to log into facebook.com, right, this data is passed back and forth in an encrypted fashion. So someone in the middle can't read that data. And this encryption is set up in what's called a TLS handshake. So you have a diagram on the side of what a typical handshake looks like. The client or the browser initiates it by sending a client hello that contains cryptographic algorithms that are supported by the client. These are referred to as the ciphers. Some versioning details about what the TLS handshake should look like. The supported extensions, a list of compression methods, and other session-related parameters as well. In response, the server sends back its own server hello message when a satisfactory set of algorithms have been selected and they've been confirmed. Subsequently, after doing all of this, the server and client will proceed to verify each other's authenticity via digital certificates and derive session keys to tunnel the remaining traffic in an encrypted fashion. Now, one thing to note, these packets are heavily reliant on the packages and methods and operating systems that are used to derive it. So when building these applications, the selected packages and the libraries and what platform we choose to run our application on severely influence these parameters in these packets. Cool. So let's talk about what JA3 does now that we know what the TLS handshake looks like. So JA3 was a tool that was introduced by Salesforce in 2017. And the goal is really to fingerprint these TLS client hello packages, right? So that first initial bit of that TLS handshake where the client sends its client hello message, we want to fingerprint those. And we will look at specific field in that TLS client hello packet. And these fields are the TLS version, the supported ciphers, the extensions, right, the elliptic curves or the supported groups, and the elliptic curve point format. So these 5 fields are what we grab out of these TLS client hello packets, and then we will aggregate them together and hash to produce that final fingerprint. And the reason we did this is it's quite useful to identify unusual clients within a network. So by taking these fingerprints, we can actually group client applications like Google Chrome browsers and Internet Explorer browsers and your system, like clients like Slack and all of these things can be grouped together within a network by just fingerprinting this portion of that TLS handshake. So now that we've talked a little bit about what JA3 does, let's talk a little bit about what JARM does. So JARM, as opposed to JA3, is a server-side fingerprinting technique, meaning that JA3 was used to passively fingerprint client-side applications by looking at specific fields in their TLS client hello packets. JARM is an active fingerprinting tool that reaches out to servers and grabs their server responses, meaning they'll grab their server hellos and fingerprint or grab certain fields from those server hellos and fingerprint those fields to identify that the hash or the fingerprint for a specific server. So it's used to fingerprint server hellos in the SSL handshake. So as opposed to the 5 fields in the TLS client hello packet or in JA3, in the server-side hello packet, JARM just looks at 3 fields: the TLS version that gets sent back, the cipher that was chosen by the server to continue the rest of the handshake, and the TLS extensions that are supported as part of that server hello response. So let's talk a little bit about how JARM works. So JARM works by actively sending 10 customized TLS client hello packets to a target server and then capturing that server's responses. And these client hello packets are specifically designed and engineered to draw out the most unique responses from a target server. So asking it questions like, does this server support TLS 1.3? If we order the ciphers a specific type of way, which cipher would it pick? What if we shuffled them around and maybe even dropped some? Which cipher would it pick then? So asking it questions like this, grabbing those responses, and then aggregating them together to give that JARM fingerprint is the process it follows. And we can see the configuration selected for these 10 TLS client hello packets in the PyJARM implementation on the slide. So PyJARM is the Python implementation of JARM that was open sourced by Palo Alto Networks. And we can see the kind of the nature of these configurations for each of these client hello packets that get sent out. And after grabbing all of these responses, it aggregates it together JARM aggregates it together to give a fingerprint. So what exactly is this fingerprint? This fingerprint is actually a fuzzy hash fingerprint that is made up of 2 consecutive 30-character and 32-character blocks. The first 30-character block is actually the TLS version and the cipher for each of the server hellos that got sent back. So each of these 3 characters represents that one response for that specific hello packet. And the second block is the SHA-256 hash of the TLS extension. So this is a truncated version. It's not the complete version, but that makes up that second block. And then when you concatenate these together, you have that 162-character block that is the JARM fingerprint. And you can see the figure in the slide for where that line is drawn for a few different domains that were fingerprinted using JARM. So what JARM is used for, and now that we see in that picture, right, it's useful for 2 things. The first is we can group servers together by configuration. So as you can see in the slide for Google, YouTube, and Blogger, that JARM fingerprint is actually the same. And this is because the infrastructure for these, or the underlying operating system and application that these servers run on top of, are actually similar. So we can group these servers together. We can say these group of servers belong to Google, and these belong to Netscope, these belong to Apple, etc. And the second is we can identify malware command and control infrastructure in popular attack frameworks like Cobalt Strike and similar C2 infrastructure that's normally very difficult to detect and defend against. We can easily identify using a fingerprinting technique like this, like JARM. And the rest of these presentation will be focused on JARM. We'll touch base with JA3 a little bit later on, but most of the work we're doing here and the research is around JARM. So what are some challenges with using JARM? What are some weaknesses with this implementation that you need to keep an eye out for when you run a JARM scan or a JARM fingerprint in your defenses? As we mentioned earlier on in the presentation, JARM and JA3 and TLS fingerprinting is very much tied to the operating system, the packages and libraries, and other custom configurations of the server-side application. For example, Cobalt Strike JARM is actually the JARM for Java 11 TLS stack. So when we're on the internet and we're trying to identify Cobalt C2 infrastructure and we identify the Cobalt Strike C2 JARM, we're actually identifying that Java application that's running on that specific package or using that specific package. So when would this cause issues? Firstly, when you're using it by itself, it can cause a few detection issues. Firstly, there can be a higher rate of false positives. As we shown in the example above, it can be quite difficult to identify exactly what we're looking at as opposed to the framework infrastructure or framework and operating system that it's running on. And this is especially enhanced when we're looking at common libraries or tools that use common libraries and operating system sockets for communication, because you're pushing that further down, which makes it a little bit hazy to identify. Secondly, we can see that switching some configurations around, or maybe using a proxy or a load balancer, would result in a completely different fingerprint, which makes this even more unreliable when it's using it by itself. Although JARM plus other intelligence has been proven to be quite useful, it is as part of a grouped detection scheme, as part of a grouped approach. So while it's not completely trivial to get a new JARM fingerprint, as opposed to mechanisms like the user agent string, which is just a header in the request you can change, JARM by itself is actually not bulletproof as well. So now that we've talked a little bit about what JARM is, what the weaknesses and challenges are, and how it works, let's talk a little bit about how these server-side changes or these server-side tweaks, specifically in TLS version and the cipher supported by the server, would affect the overall JARM fingerprint. So this was a test that was run on a Mac OS system using PyJARM for fingerprinting. PyJARM is a library implementation of JARM that was introduced by Palo Alto Networks. And what we did was we used the SSL library in Python to cycle through the supported TLS versions and ciphers, and we spun up a server and we fingerprinted that using JARM or PyJARM, and we tried to see what the resulting JARMs were. And as you can see from our findings, changing the TLS version and the supported cipher server side actually changes the JARM fingerprint a decent amount. So how can we use this to evade JARM? Now that we know that changes in server-side configs can actually result in a completely new fingerprint, how can we use this knowledge as a red team operator or a penetration tester to give ourselves the upper hand when evading JARM fingerprinting? So before we get into evading JARM fingerprinting, let's talk a little bit about JA3 transport. JA3 transport was presented in 2019 by the CU Cyber team, and it's a Go library that's specifically used to evade client-side JA3 fingerprinting. So if you remember from our initial presentation of JA3 is used to passively fingerprint client hello packages to identify what kind of application made that request. So things like your browser versus a Slack client or some malware that may be on your system. right? JA3 can be a really useful tool to fingerprint and identify these client applications. JA3 transport is a library that you can incorporate in a Go executable or a Go binary to evade this kind of fingerprinting. In this talk, we'll present JARM randomizer, which is the server side. You can really think of it as the server side equivalent for JA3 transport. And it achieves evasion by cycling through these supported configurations to give the desired JARM fingerprint for red team operators and penetration testers. So let's talk a little bit about JARM randomizer itself. At the heart of it, it cycles through the supported configuration server side to enable a different fingerprint or a different desired fingerprint for the operator. Some dependencies are pipenv. It's written in Python 3.9, so you need to have that installed when you run this. PyJARM, Shodan, and PyBinary are also required for additional functionality. So the current features for this tool are to iterate and identify valid configurations during setup. So this is really useful, so you don't have to do that work yourself. Secondly, it'll check the generated or the valid JARMs for your system on Binary Edge and Shodan to give you some more insight on the usage of the specific JARM that you want. Thirdly, you can cross-check these specific JARMs against a known red team tool list to make sure that you're not using the ones that have been associated with public command and control tools. And finally, it gives you the ability to cycle through or rotate configurations at specific intervals so you make sure you have a different JARM fingerprint at the desired time interval. So where is the placement of a tool like this? So really, it is a Python proxy that is meant to be placed in front of a command and control server. So as you can see, without the randomizer, this would be what a typical deployment would look like in an engagement. With the randomizer, you'd put this Python proxy on the same system or a different system that's in line with that traffic, right? And you can use this alongside Cobalt Strike to evade fingerprinting of the Cobalt Strike tool itself. You can use JARM randomizers to cycle through these configurations. So let's talk a little bit about the setup process and what this tool gives you when you do that setup. The setup is actually required for this tool to run, so it can identify the supported configurations on the system, and it also helps you lay that kind of groundwork that's required to run the proxy successfully later on. And what it does is, the first thing is it grabs those list of ciphers that supported on the system, right? And then it finds all the possible JARMs by rotating through the TLS versions and the supported ciphers, and it validates them. And once it validates them, it tells you how many JARMs that it found that it can support on the server side and how many TLS cipher pairs generated those JARMs. And if you've supplied an API key for Binary Edge or Shodan, it grabs those metrics for the JARMs and the usage on the internet, and it'll give you some statistics on that as well. And once it's laid all this out, it'll give you the command you need to run so you can have that proxy deployed and ready. So let's talk a little bit about one test run on a Mac OS system. And let's analyze some of the findings. So on a Mac OS system, we identified 31 possible JARMs across 48 TLS cipher pairs. And in this table, we can see the top 5 JARMs when sorted by occurrence in Shodan, right? And we've also co-referenced or correlated the JARM fingerprint against the known list of red team tools from a publicly available repo to grab that usage as well. So the important things to note here are 2 TLS and cipher pairs can generate the same JARM. As you can see, for the 5th entry, 18 TLS cipher pair instances actually generated the same JARM fingerprint. And while it might not be completely obvious here, because this is showing the top 5, but if you saw that complete list, there is a sway towards Python product. And lastly, you can see that second JARM field actually matched 5 red team tools. So as a red team operator, you might want to keep that in mind and maybe avoid that specific entry to maintain operational security. And all of these, the binary edge showed on the red team tools are all supported by the randomizer itself. So these are statistics you can pull out if you wanted to run this on your system and get some stats back. So let's talk a little bit about the 2 use cases that we feel the field really benefit from. There is a configuration file present in that repository, so if you wanted a specific configuration, you can achieve it. But these are the 2 that we feel are very important for people in the field. The first is to serve one preferred JARM. So you've done that analysis that we saw in that previous slide, and you found that JARM fingerprint that you want to run that meets your criteria for operations. So you can grab that configuration, set it in that configuration file, and it'll run for that JARM fingerprint for as long as you want. The second is maybe you want to cycle through these configurations every 5 seconds or every day or every month. You can set that in the configuration file as well, and it'll cycle through these supported configurations with a little bit of downtime to swap out or restart that server, and you'll have that a new JARM that's supported on your system as well. So what are some limitations from using this tool? One, there's a finite number of signatures. Like we presented earlier, and we've talked about many times in this presentation, these fingerprints are very reliant on the underlying operating system, the packages libraries. So you will not have that infinite space where you can generate that specific JARM that you want. You are limited by the signatures that are supported on your system, right? Secondly, the client compatibility check is very much required. So what we've done here is, or in the setup process, we've checked the server. The server has checked whether it can negotiate a successful handshake itself with a server that it stood up. And if it passes that check, then we give that a check mark for those configurations. But you also want to make sure that the client you're packaging and deploying on these red team engagements or these penetration test assessments, you want to make sure that client can also successfully make a handshake with the Python proxy to make sure there isn't an issue setting up a connection there. Thirdly, JARM randomizer does not make any changes or have any type of support to mangle the traffic itself to avoid detection, right? So the traffic itself might be identified by other behavior-based methods or other C2 traffic identification methods. And lastly, and this is the most important one, this is not exhaustive yet. Right. We have done a decent amount of work here, but it's not complete. This is meant to be a step in the direction to fully evade fingerprinting. And we feel that this is important enough to share with the community, but there's definitely a lot more work that needs to be done here. Right. And some of the work that we'll do to improve this is one, we'll scale to generate a larger list of signatures for sure, to tackle number one. Secondly, we would like to have functionality where you can just point this at a server and say, I want that server's JARM, and you can achieve that configuration as well. And lastly, we're trying to come up with, and this is more on the defensive side, we want to come up with a TLS-based fingerprinting technique that is more difficult to evade than JARM and J3. And both of these are amazing to include. Are great to include as part of your tooling infrastructure, and we want to add on and improve these as well. Finally, we want to give amazing recognition for the Salesforce engineering team for JN3 and JARM. They have done an amazing job at identifying these phenomena and packaging them up or releasing them for the community. And they also did a great job of documenting and coming up with cool GIFs as part of their blog, which I shamelessly borrowed for this presentation. and the CU Cyber team for JA3 Transport, which these two teams really kind of laid out the groundwork to do this project and bring JARM Randomizer to you guys. And in the spirit of matching JA3, JARM, and JA3 Transport, we are open sourcing JARM Randomizer, and we hope you guys, take it, play around with it, make changes as well. So let's talk a little bit about what the takeaways are, and we can conclude this presentation. So the takeaways are, first, the JA3 and JARM. What are they? How we can use these in our systems, how they work, and talked a little bit about the background for these. Secondly, we talked about how JARM is really not reliable as a lone tool by itself to fingerprint these servers, right? Thirdly, we showed that just minor server-side changes and configuration tweaks actually result in different JARM fingerprints. And finally, we packaged all of this up and presented it as JARM Randomizer, a tool that you can use to cycle through these configurations, and red team operators and penetration testers can actually use to maintain operational security. And finally, this is an active area of research that we very much are involved in. So keep an eye out on our blog for the latest from our research and tools and other interesting stuff as well. Finally, if you need to follow me, reach out to me, message me. That's my Twitter handle. My LinkedIn is right there. GitHub link will also be available for you guys. So feel free to reach out on any of these. And if you want to keep up with us and what we do here at Netscope, follow our blog and see what cool stuff we have. Awesome. Thank you very much for your attention. I hope you got something out of this presentation, and I hope that you enjoy the rest of your time here at Hack in the Box 2021 Amsterdam.
And with that, we have come to the end of the COMMSEC track for this year's HITB Amsterdam. We would explicitly like to thank all the speakers, crowd fans, and all participants. Have a wonderful day, and until we meet again, bye-bye. See you next year.